1929 UTC. A satellite, orbiting 35,786 kilometers above Earth, records a final electronic whisper from a missing aircraft. Not a distress call, not a scream over the radio, not a mayday, a handshake. 7 pings had already passed between the aircraft and an Inmarsat satellite that night. This was the 8th, the last. And for years, investigators treated it as proof of something specific, something conclusive. But what if that final handshake didn't mean what we think it did? At 0041 local time on March 8, 2014, a Boeing 777 operating as Malaysia Airlines Flight 370 vanished from civilian radar after departing Kuala Lumpur for Beijing. 239 people on board. No distress call, no confirmed debris, no verified crash site, just silence. Then, hours later, something strange. The aircraft's SATCOM system responded to an automated satellite log-on interrogation, a handshake. At 8:19 a.m., Malaysian time, nearly 7 hours after takeoff, that final signal was recorded. And for many, that final ping drew a line on a map, a line that pointed south, deep into the Indian Ocean. But here's the question that has haunted analysts ever since. Was that last handshake evidence of controlled flight? Or was it the sound of a dying system powering up one final time? Because if the interpretation is wrong, even slightly wrong, then the search area could have shifted by hundreds of kilometers. And that means everything changes. Before we move forward, if you're drawn to investigations like this, if you want the data, not just the headlines, consider subscribing. This channel exists to slow down the noise and examine the evidence frame by frame. If you have a theory about that final ping, whether it proves deliberate flight or system failure, share it below. Because sometimes the best breakthroughs don't come from official reports. They come from the questions no one stops asking. Now, let's rewind. Because to understand that final handshake, you have to understand what actually vanished that night. It begins routinely. March 8, 2014. Malaysia Airlines Flight 370 departs Kuala Lumpur International Airport at 12:41 a.m. local time. Destination, Beijing. Aircraft, Boeing 777-200ER. Fuel on board, enough for roughly 7.5 hours. Souls on board, 239. The climb is normal. Cruise altitude, 35,000 feet. Speed, steady. Weather, clear. At 1:19 a.m., the last routine radio transmission is heard. Good night, Malaysian 370. It's calm, controlled, unremarkable. 38 seconds later, the aircraft's transponder, the device that broadcasts identity and altitude to civilian radar, goes dark. No distress call, no squawk code, no warning, just absence. But the aircraft does not vanish. Military primary radar, which tracks raw returns without relying on transponders, continues to paint a target. And what it shows changes everything. Instead of continuing northeast toward Beijing, the aircraft turns sharply left, west, crosses back over the Malay Peninsula, passes near Penang Island, then heads northwest into the Strait of Malacca. This is not drift. It is a controlled, deliberate turn. Altitude changes appear minimal, speed consistent. Someone, or something, is flying that aircraft. At approximately 2:22 a.m., military radar contact is lost over the Andaman Sea. After that, nothing from radar, no debris fields detected, no confirmed emergency beacon. And here's where the timeline fractures. Because while radar saw silence after 2:22, a satellite 36,000 kilometers above Earth was still hearing something. At 2:25 a.m., just 3 minutes after radar contact ends, the aircraft's satellite data unit, part of its SATCOM system, performs what engineers call a log-on request. It reconnects with the Inmarsat 3 F1 satellite. Why? Two possibilities immediately emerge. 1. The system lost power and rebooted. 2. The aircraft crossed into a region requiring renewed handshake authentication. Investigators later leaned toward a power interruption. But already the timeline is bending, because if power was interrupted, even briefly, what caused it? An electrical failure? Manual shutdown? Fuel feed anomaly? The SATCOM system continues to exchange automated hourly handshakes. 3:41 a.m., 4:41 a.m., 5:41 a.m., 6:41 a.m., 7:41 a.m. Each ping does not reveal position directly. Instead, it provides two crucial measurements. Burst timing offset, BTO, how long the signal took to travel. Burst frequency offset, BFO, the Doppler shift, hinting at relative motion. These are not GPS coordinates, they are mathematical shadows. But those shadows can draw arcs across the planet, and they do. By analyzing BTO values, engineers determined that the aircraft must have been somewhere along a series of arcs radiating from the satellite. Each handshake forms a widening ring. North, toward Central Asia, south, into the vast southern Indian Ocean. The BFO data, frequency shifts, suggest the aircraft was moving away from the satellite in its final hours, southbound. This interpretation becomes the foundation of the largest and most expensive search in aviation history. More than 120,000 square kilometers scanned, underwater sonar, autonomous vehicles, deep sea mapping, and yet, no main wreckage. Only scattered debris years later, confirmed pieces of a Boeing 777 flaperon found on Reunion Island in July 2015, and additional fragments along African coastlines. Physical evidence that the aircraft did enter the ocean, but not precisely where the final handshake arc suggested. And that brings us back to the moment that matters most. 8:19 a.m. The final handshake. Was it evidence of controlled flight until fuel exhaustion? Or was it the echo of a system collapsing mid-air? Because if the aircraft was already descending rapidly when that last ping occurred, then the arc might not mark the end point. It might mark something else entirely. To understand that possibility, to truly examine what that last signal means, we need to break down the system itself. How satellites measure distance without GPS. How Doppler shift betrays motion. How a dying engine can alter the mathematics. Because the answer may not be in the location of the ping, but in the shape of its frequency curve. And that is where the mystery deepens. The final handshake. Investigators treated it like a digital footprint, proof the aircraft flew for nearly 7 hours after disappearing from radar. But what exactly is a handshake? What does it measure? And more importantly, what does it not measure? The aircraft was equipped with a satellite communication system, SATCOM, not GPS tracking, not live positional telemetry, just a data link designed primarily for voice calls and routine system messages. The satellite involved was Inmarsat 3F1, positioned in geostationary orbit above the Indian Ocean, 36,000 kilometers above Earth. It doesn't move relative to the ground. It simply listens. Every hour, if idle, the aircraft's satellite data unit responds to a brief automated interrogation signal, a ping, a handshake. This exchange produces two critical numbers: BTO, burst timing, offset, BFO, burst frequency, offset. Those two metrics built the Southern search. But here's where precision matters. Burst timing offset measures how long it takes for the signal to travel from aircraft to satellite and back to a ground station. Signal travel time equals distance, but not direction. So investigators could determine that at 8:19 a.m., the aircraft was somewhere along a curved arc equidistant from the satellite. Not a point, an arc stretching thousands of kilometers, north into Central Asia, or south into the remote Indian Ocean. BTO narrows the radius. It does not choose the hemisphere. So how did investigators decide it was south? That's where BFO comes in. Burst frequency. Offset measures Doppler shift. When something moves relative to a receiver, frequency changes. Higher pitch if approaching, lower pitch if moving away. The same effect you hear when a siren passes you on the highway. In this case, the satellite detected subtle frequency shifts in the aircraft's transmissions. By analyzing these shifts, engineers concluded the aircraft was moving generally away from the satellite during the final hours. And because of the satellite's fixed position over the equator, movement away implied a southern trajectory. Models were run, simulations built, assumptions tested. The consensus: the aircraft likely flew south until fuel exhaustion. At approximately 8:19 a.m., fuel ran out, engines flamed out, autopilot disengaged. The aircraft entered a descent. That final handshake, interpreted as a routine automated log-on after power interruption, became the last marker. Case closed? Not quite. The final handshake at 8:19 wasn't identical to the earlier ones. It consisted of two partial exchanges, and the BFO values in that final transmission were unusual, higher than expected. Some independent analysts have argued that those frequency values suggest a rapid descent at the moment of transmission, possibly a steep, uncontrolled dive. Others caution that modeling Doppler shift during unstable power conditions is complex. Here's the nuance. When both engines fail on a Boeing 777, electrical systems switch configurations. The auxiliary power unit, the APU, can automatically start if certain power thresholds are crossed. If that happened during fuel exhaustion, it could have triggered the SATCOM system to reboot, meaning the final handshake may not represent steady cruise flight. It may represent a moment of transition, a system coming back online mid-fall. And that distinction matters, because if the aircraft was already descending rapidly at 8:19, then the impact point could be significantly north of the final arc used to define the search zone, not hundreds of meters, potentially dozens of nautical miles. Every model rests on assumptions. Assumption 1, the aircraft maintained controlled flight until fuel exhaustion. Assumption 2, the final BFO readings reflect normal cruise conditions. Assumption 3, no major system anomalies distorted frequency calculations. But what if one of those assumptions is wrong? What if the final handshake wasn't evidence of endurance, but evidence of collapse? No cockpit voice recorder has been recovered, no flight data recorder, no confirmed debris field pinpointing impact coordinates, just mathematics. Arcs drawn from time delays, velocities inferred from frequency drift. It is elegant, it is scientific, it is probabilistic, and probability is not certainty. What if the engines flamed out minutes before 8:19? What if the aircraft entered a steep descent before the handshake completed? What if the BFO spike reflects vertical velocity, not cruise trajectory? What if the arc is correct, but the endpoint interpretation is not? The southern Indian Ocean search zone was built on the assumption of controlled flight. But if the final handshake represents instability, then the last known arc may be a mathematical illusion, or at least incomplete. So now the investigation forks. One path, controlled glide into remote ocean. The other, uncontrolled descent beginning before the final signal. Both consistent with some data, neither fully proven. And that brings us to the human layer of this mystery. Because behind every data point was a cockpit. Behind every frequency curve, two pilots. And behind every assumption, a decision. Inside that cockpit, sometime before dawn, the fuel state would have become unavoidable. On a Boeing 777-200ER, fuel endurance that night was estimated at roughly 7 hours and 30 minutes, based on the filed flight plan and load data later analyzed. Departure, 12:41 a.m. Projected fuel exhaustion window, shortly after 8 a.m. local time. By 7:41 a.m., the second-to-last satellite handshake had been recorded. At 8:19 a.m., the final partial exchange occurs. Somewhere between those two timestamps, the engines likely began to flame out. And here's what that means mechanically. The Boeing 777 is built with layers of redundancy. When the first engine flames out, electrical power shifts. When the second engine flames out, primary generators are lost. For a brief period, the aircraft relies on the ram air turbine, a small deployable device that uses airflow to generate limited emergency power. Then, if conditions permit, the auxiliary power unit, the APU, can automatically start. That startup takes seconds, but in that window, systems drop offline, including SATCOM. If the satellite data unit lost power and rebooted as the APU came online, it would automatically attempt to log back onto the Inmarsat network, which is exactly what appears to happen at 8:19 a.m. But here's the tension. Did the engines flame out before the final handshake? Or did they flame out after it? Because the timing of that sequence determines whether the aircraft was still in controlled flight or already descending. The final transmission consists of a log-on request from the aircraft, a partial log-on acknowledgement, then silence. No further hourly pings, no sustained communication, just a brief reconnection attempt. Investigators from multiple agencies later concluded that this likely reflects a power interruption consistent with fuel exhaustion. But the data is not a cockpit recording. It is inference layered over system behavior, and one subtle detail stands out. The BFO values in the final transmission suggest a significant downward rate of change. Some analyses estimate a descent rate potentially exceeding 12,000 feet per minute. Others caution that these estimates depend heavily on assumptions about autopilot engagement and system stabilization during reboot. So the human question becomes unavoidable. Was someone flying the aircraft until the very end? Or did the aircraft enter an uncontrolled descent once both engines flamed out? If autopilot remained engaged until fuel exhaustion, the aircraft would likely maintain altitude until thrust loss. At dual engine flameout, the autopilot would disengage. Without manual input, the aircraft could enter a phugoid oscillation, a long, undulating glide pattern. If manually controlled, a pilot could attempt a glide. A Boeing 777 at cruise altitude has a glide ratio of roughly 17:1. From 35,000 feet, that translates to over 100 nautical miles of potential forward travel. But that assumes conscious control, stable trim, intentional glide management. No evidence confirms whether that occurred. No debris field geometry has conclusively shown a long glide pattern, and the main wreckage remains undiscovered. There was no distress call, no emergency transponder code, no cabin communication intercepted, 239 people, and not a single confirmed transmission after 1:19 a.m. That absence is as loud as any signal. No smoke report, no decompression alert, no Mayday, just controlled silence. Then digital whispers, and that silence fuels competing interpretations. One possibility: deliberate action inside the cockpit earlier in the flight, followed by hours of controlled flight southward. Another, incapacitation event, hypoxia, depressurization, leading to an aircraft flying on autopilot until fuel exhaustion. Both scenarios are consistent with portions of the data. Neither is definitively proven. Somewhere below that final arc lies ocean floor over 4,000 meters deep. Cold, dark, pressurized. Debris confirmed years later, a flaperon found on Réunion Island in July 2015, verified that the aircraft entered the ocean. Ocean drift modeling suggests southern Indian Ocean origin. But drift modeling also carries uncertainty bands spanning thousands of square kilometers. Families still wait for certainty, and certainty depends, in part, on how we interpret 819. Was that final handshake the sound of a plane cruising steadily into emptiness? Or the electrical reflex of a machine losing power mid-descent? The difference is not academic, it redraws the map. Because now we arrive at the fork. One path says the aircraft remained controlled until the very last drop of fuel. The other suggests instability began before the final signal completed. And that brings us to the competing theories. Each built on the same data, each drawing different conclusions from the same 8 pings. 8 pings, 2 numbers per ping, thousands of square kilometers of ocean, and 3 major interpretations. Each one built on the same satellite data, each one drawing a different ending. So let's lay them out, cleanly, clinically, like an evidence board. No drama, just models. The aircraft remained on autopilot, flying south in stable cruise until fuel exhaustion around 8:19 a.m. When the engines flamed out, the aircraft descended rapidly into the southern Indian Ocean near the final satellite arc. Supporting points: consistent hourly handshakes from 2:25 a.m. to 8:19 a.m. BFO data generally indicating movement away from the satellite fuel endurance calculations aligning with final ping timing. Ocean drift modeling, consistent with southern Indian Ocean origin of confirmed debris. Under this model, the final handshake likely occurred just as the APU restarted following dual-engine flameout. The aircraft then entered a descent, possibly steep, possibly uncontrolled, within minutes. Search efforts between 2014 and 2017 focused on areas along the southern arc, consistent with this scenario. Over 120,000 square kilometers scanned, no confirmed wreckage field. That absence raises a question. If the model is correct, why hasn't the main debris field been found? Is it simply depth and terrain complexity, or is the starting assumption slightly off? The aircraft may have already been descending rapidly when the final handshake occurred. The 819 signal may reflect a mid-descent power event rather than steady cruise. Elevated BFO readings in the final transmission. Possible rapid downward Doppler shift, consistent with high descent rates. Complex power transitions during engine flameout that could distort frequency interpretation. Some independent analyses suggest the aircraft could have been descending at rates exceeding 10,000 feet per minute during the final BFO measurements. If that's true, the arc derived from steady flight assumptions could be misplaced. Even a small timing difference between engine flameout and handshake completion could shift the impact zone significantly north of the previously searched areas. But there's a caveat. Modeling Doppler shift during unstable electrical conditions is extraordinarily complex. Satellite movement, aircraft antenna characteristics, oscillator drift, temperature effects. Small errors compound quickly. This theory doesn't reject the southern route. It questions the precision of its endpoint. The northern arc cannot be ruled out with absolute certainty, though it is widely considered less likely. Early in the investigation, both northern and southern arcs were viable. The northern route would have taken the aircraft over Central Asia. However, BFO data trends were more consistent with southern movement. No confirmed radar returns along the proposed northern corridor. No debris consistent with a land crash discovered across the vast northern arc. Still, the northern route highlights a critical truth. The satellite data alone did not provide latitude directly. It required interpretation layered on Doppler analysis. And interpretation carries uncertainty. Everything hinges on seconds. When exactly did the engines flame out? When did the APU start? At what moment did the SATCOM system reboot? And was the aircraft level climbing or descending during that reboot? If engine flameout occurred before 819 and descent began immediately, the final BFO spike may reflect vertical velocity. If flameout occurred after the handshake completed, then the arc remains largely accurate. The difference may be less than 2 minutes. 2 minutes at cruise speed is roughly 15 nautical miles. 2 minutes during uncontrolled descent changes the geometry entirely. Known. Aircraft deviated west after last radio transmission. Military radar tracked it until 2:22 a.m. 7 hourly satellite handshakes occurred. Final handshake at 8:19 a.m. Debris confirmed from Boeing 777 found along western Indian Ocean coastlines. Unknown. Exact impact coordinates. Descent profile. Cockpit conditions. Whether flight was manually controlled at the end. No cockpit voice recorder. No flight data recorder. No primary wreckage, just arcs. Just frequency curves. Just probability. The satellite handshake is both the strongest piece of evidence and the most fragile. It defines the search, but it depends on assumptions about system behavior during a catastrophic moment. If those assumptions are even slightly misaligned, then the ocean may be hiding the aircraft just beyond where we looked. So the question shifts, not where did it go, but how certain are we that the final handshake means what we think it means? Because in complex systems, the final signal is not always the final truth. And in this case, the last whisper from space may be telling a more complicated story. Years passed. The Southern Indian Ocean search, one of the largest and most expensive in aviation history, officially concluded in 2017. More than 120,000 square kilometers scanned. Deep water autonomous vehicles mapping seafloor ridges 4 kilometers below the surface. Nothing conclusive. No fuselage, no black boxes, no definitive debris field. Only absence. Then, a shift. In 2018, Ocean Infinity, a private marine robotics company, launched a renewed search under a no-find, no-fee arrangement with the Malaysian government. The target zone was slightly north of much of the earlier search area. Why? Because independent reanalyses of satellite data suggested the aircraft may have descended earlier than assumed. Some researchers propose that the final BFO values indicated a high rate of descent before the 8-19 handshake completed, meaning the impact zone could lie outside the highest confidence search box. Ocean Infinity scanned approximately 112,000 square kilometers in a matter of months. Again, no confirmed wreckage. But here's what matters. The reanalysis didn't discard the southern arc. It questioned the precision of the endpoint. And precision is everything in deep ocean recovery. Confirmed debris, including the flaperon found on Réunion Island in July 2015, provided physical evidence the aircraft entered the Indian Ocean. Subsequent fragments washed ashore in Mozambique, Tanzania, Madagascar. Oceanographers ran backward drift simulations. Most models pointed toward the southern Indian Ocean, but ocean currents are chaotic systems. Small variations in wind, surface current velocity, and seasonal shifts can significantly alter reverse drift estimations. Drift modeling narrows possibilities. It does not pinpoint coordinates. So again, the interpretation of 8-19 becomes central. In recent years, analysts have re-examined oscillator warm-up drift during SATCOM reboot, satellite ephemeris precision, aircraft antenna, gain patterns, power transient effects during APU start the conclusion. The southern route remains the most probable, but the impact location band may be narrower and slightly repositioned compared to earlier models. In 2023 and beyond, renewed discussions emerged about launching another search effort, contingent on refined modeling and funding agreements. The ocean floor where the aircraft is believed to rest remains partially unmapped. Ridges, canyons, sediment layers capable of concealing large structures. The aircraft is not necessarily lost. It may simply be hidden. Now we return to the handshake. If the final 8-19 signal marked a power restoration during engine flameout, then the descent profile immediately afterward determines everything. Was it steep and fast, limiting debris spread? Was it partially controlled, extending glide distance? Or did autopilot hold pitch momentarily before disengagement? Without the flight data recorder, the descent profile is modeled, not known. And models are only as strong as their assumptions. This is no longer just a search question, it's a systems question. Should commercial aircraft continuously stream critical flight data in real time? After MH370, global aviation authorities mandated longer battery life for underwater locator beacons. Tracking standards improved. But full real-time black box streaming remains technologically and economically debated. So the final handshake is more than a mystery. It is a design flaw illuminated. An era before constant tracking. An aircraft that slipped between systems. No radar, no satellite tracking, no confirmed impact. Just mathematical inference. 2 cockpit seats, 239 lives, an empty stretch of ocean. 8 pings. The final one at 8:19 a.m. Was it the steady pulse of a jet flying until the last drop of fuel? Or the electrical gasp of a machine already falling? The southern Indian Ocean is vast, but it is not infinite, and history shows that wreckage long thought unreachable can eventually be found. The question is not whether the ocean holds the answer. It's whether we are interpreting the last signal correctly. Because if the final satellite handshake does not mean what we think it means, then the search is not over. It's simply aimed a few miles in the wrong direction. And somewhere beneath that silence, a data recorder waits, not broadcasting, not pinging, just holding the final seconds of truth until someone finds it.